Norman Packard is responsible for much of what we think of as chaos theory. A few years ago, he turned his attention to the creation of the world's first completely synthetic living cells. So he's got some extraordinary things to tell us about what it means when humanity begins to make our own living stuff. Please welcome to the PopTech stage, Dr. Norman Packard.
First, I'd like to talk to you about what I view as life and how I define it, and how I look at a path to create life, and what I mean by living technology. And then I'll descend into a particular project that I'm immersed in at the moment to create an artificial cell. And I'd like to close by telling you how the science to pursue this endeavor has changed from science in the past. This is the perspective that I'm starting from. Life requires self-maintenance, self-reproduction, and evolvability. Evolvability, for me, does not simply mean change. What I mean by the word evolvability is that there's some sort of inheritance and selection, natural selection going on. One might also consider other possibilities like societies or ecosystems and propose that they might, as a whole, have these properties and be not merely constituted of living parts, but themselves be living. And I think this might very well be true. Even the simplest life forms are very complex. Really, we're a long ways from engineering technology that does the basic tricks that life knows how to do. By living technology, I mean that it is defined by and enhanced by its lifelike properties. Namely, these same three properties that I referred to. These are examples. There's synthetic biology, ecological engineering, social engineering. I would even consider the internet and the World Wide Web as a candidate for living technology. It's self-maintaining. In a fairly real sense, it's reproducing itself and expanding all the time, and it's evolving. So, my example is in synthetic biology, the design and construction of new biological parts, devices, and systems, and the redesign of existing natural systems. So now I'd like to tell you a little bit about the artificial cell project. And again, the three requirements for life map into three functionalities that are needed for this construction of a cell. One is a container, and one is a metabolism that harvests energy. And the metabolism typically has waste products that it exudes. And then the last is an informational component. And it's this informational component that gives this entity its evolvability. Let me tell you, after spending hours looking at the microscope, it is a jungle down there. And there's lots and lots of different morphologies, a huge universe of morphologies, a combinatorial diversity of structures. And what we want to do is to use that diversity to drive the discovery of the right conditions for the artificial cell. So to do this, we use this evolutionary approach where we use a form of a genetic algorithm to search this space of vesicle morphologies combined with chemical reactions. And so we define target functionality, and this actually generates a context that's very messy. Here the complexity gives this genetic algorithm the elbow room to actually discover pathways to solutions. So now I want to close by telling you how I think this science that we're doing in these projects is different than traditional science. And to do this, I want to make a distinction, a contrast between two kinds of science. One I'm calling modern science, which I'm referring to as strong science. The other I'm calling postmodern science. This is the science that I will argue is weak compared to modern science. This modern science is traditional science as epitomized by scientists ranging from Galileo through Einstein and thousands of scientists in between. And from the laws of nature, you can derive what nature is going to do. Examples here are movements of the planet, atomic spectra, design of all kinds of technology from cars to computer to bombs. I want to contrast the strong science with weak science where natural law is not quite so powerful, in the sense that you can write it down, but there are phenomena that you can't derive from it. Phenomena that are, in principle, underivable. And these are strongly emergent properties. Chaos is an example, fluid turbulence is an example, life itself is an example, consciousness is another example. And in each of these examples, a phenomenon, like life, builds on a substrate. Consciousness builds on a substrate that is itself life. Life, and many phenomena like life, interesting emergent phenomena, live at the edge. This has strong ramifications for engineering. You have to give up strong derivability, learn to harness emergence, and live with the uncertainty that comes with it. Thank you very much.